Vibrating universe. The concept known as string theory stands as one of the boldest endeavors in contemporary physics, yet it continues to be shrouded in mystery and sparks intense debate. What makes it so fascinating is its daring attempt to answer the ultimate question: how do all elements of the universe, each particle, each force, every interaction, fit into a unified framework? Humanity's journey to comprehend the core essence of reality has been ongoing for centuries. Philosophers, scientists, and great thinkers have long pondered what the universe is truly made of and how it fundamentally operates. In the 20th century, significant breakthroughs came with the advent of quantum mechanics and the theory of general relativity. Yet, despite their profound successes, these two foundational models have never seamlessly merged. String theory is a daring and innovative proposition aimed at bridging that gap, merging the intricate quantum domain of the minuscule with the grand structure of spacetime described by general relativity. Envision trying to assemble a flawless and stunning image of the universe using two jigsaw puzzles. One represents the quantum realm of subatomic particles, governed by strange and often counterintuitive rules. The other represents the vast cosmos, from planets and stars to the very continuum of spacetime itself. The issue lies in the incompatibility of these puzzle pieces. One model is based on discrete, probabilistic interactions among particles. The other describes the universe as smooth and continuous. String theory suggests a new path forward. The answer lies in identifying the tiniest components of existence, infinitesimally small vibrating strings that constitute the foundational elements of all matter and energy. The origins of string theory can be traced back to the 1960s, when physicists sought to decode the behaviors of subatomic particles. During this era, particle physics was rapidly advancing, with new particles being discovered almost annually. At that time, these particles were thought to be point-like, essentially without internal structure, mere dots in space. However, as researchers delved deeper, they began encountering theoretical inconsistencies. Equations describing point particles began to fall apart under extreme conditions, resulting in nonsensical predictions like infinite energies. This signaled the need for a more fundamental explanation. That's where string theory came in. The first hints emerged from studying the strong nuclear force, the force that binds atomic nuclei. The complex mathematical expressions describing this force bore a striking resemblance to the equations for vibrating strings. This unexpected connection paved the way for a revolutionary theory. In string theory, the basic constituents of reality are not point particles, but minute vibrating strings. Much like the strings of a musical instrument can produce various notes through different vibrations, strings in this theory can oscillate in diverse patterns. Each vibrational mode corresponds to a distinct particle, such as an electron or a quark. What string theory proposes is that every particle and force we observe is merely a different expression of the same fundamental object, vibrating strings. This idea marks a significant shift from prior conceptions. Rather than viewing particles as tiny dots, string theory envisions them as one-dimensional filaments capable of stretching and vibrating in numerous ways. The characteristics of a particle, its mass, electric charge, and other attributes are determined by these vibrational patterns. According to this framework, all fundamental forces, including gravity and electromagnetism, can be seen as diverse manifestations of one underlying reality. One of the most astonishing features of string theory is its prediction of additional spatial dimensions beyond the three we perceive in daily life. In this theory, the universe includes extra dimensions that are compacted or curled up so tightly that we can't detect them directly. The most basic form of string theory suggests the existence of 10 total dimensions, 9 spatial and 1 temporal. These hidden dimensions are believed to be compressed down to the Planck scale, approximately 10 circumflex minus 35 meters. To put this into context, if a string were the size of a tree, these compact dimensions would be smaller than the tiniest known particles. Though invisible, string theory asserts these dimensions have profound effects on physical phenomena. Picture a garden hose. Seen from afar, it looks like a straight line. But up close, you notice its circular cross-section. Similarly, these compact dimensions may influence the universe without being perceptible in everyday life. These extra dimensions provide the geometric framework that allows string theory to potentially unify all forces of nature. In our familiar three-dimensional world, gravity, electromagnetism, and the strong and weak nuclear forces appear distinct. But within the higher dimensional space posited by string theory, they could all be aspects of a single, unified phenomenon. A vital component of string theory is a principle called supersymmetry. Supersymmetry is a proposed symmetry that links two main categories of particles: bosons and fermions. Bosons, like photons and gluons, are force carriers, while fermions, such as electrons and protons, form matter. In a supersymmetric universe, every known particle would have a partner with a different spin. For instance, the photon, a massless boson with spin 1, would be paired with a hypothetical fermion called the photino. Likewise, the electron would have a bosonic counterpart known as the selectron. Supersymmetry would effectively double the number of particles in the standard model. Although we've yet to observe these superpartners, their existence is crucial for the internal consistency of string theory and offers a natural path for unifying the forces of nature. Without supersymmetry, string theory encounters major mathematical difficulties, particularly in reconciling gravity with quantum mechanics. One reason string theory excites physicists is that it offers a potential quantum theory of gravity. For decades, gravity and quantum mechanics have resisted unification. Quantum mechanics describes the micro-world with probabilities and wave functions, while gravity, via general relativity, depicts spacetime as a smooth continuum distorted by mass and energy. String theory bridges this divide. It introduces the graviton, a theoretical quantum particle that transmits gravity as one of the string's vibrational states. Just as a photon emerges from one vibrational pattern, the graviton arises from another. This allows string theory to incorporate gravity into the same theoretical framework as the other fundamental forces, electromagnetism, and the strong and weak nuclear forces. The notion of a quantum particle mediating gravity raises the possibility of quantizing gravity, an endeavor that has eluded researchers for decades. If string theory proves correct, it could lead to a theory of everything, a single, all-encompassing explanation for every force and particle in the universe. Despite its mathematical elegance, string theory remains speculative due to the lack of direct experimental evidence. The issue is that string theory's implications become significant only at incredibly high energies and tiny scales, far beyond the capabilities of current particle accelerators. These scales, near the Planck length, are many magnitudes smaller than what our technology can currently probe. Nonetheless, scientists hope that advancements in tools like the Large Hadron Collider LHC might one day uncover indirect signs of string theory's validity. For instance, detecting supersymmetric particles would support key predictions of the theory. Additionally, string theory offers insights into black hole dynamics and the quantum structure of spacetime, phenomena that could be tested through astrophysical observations. Meanwhile, string theory remains a vibrant area of theoretical inquiry, yielding deep revelations about spacetime and the basic forces that shape our cosmos. Whether experiments will ultimately validate it remains uncertain. Yet its mathematical beauty and conceptual unity make it one of the most captivating theories in contemporary physics. String theory presents a profound vision of the cosmos in which all particles and forces are woven into a single tapestry, composed of minute vibrating strings. These strings may hold the key to unlocking the universe's most enduring mysteries, from the essence of gravity to the unification of nature's forces. Although experimental confirmation is still pending, string theory's potential to address physics's deepest questions makes it an exhilarating frontier of research. Even if it doesn't become the final theory of everything, it has already transformed our approach to understanding the universe, opening fresh paths of discovery and redefining what might be possible. Quantum tunneling. Quantum tunneling is one of the most astonishing and counterintuitive phenomena found in quantum physics. It turns our everyday understanding of how the world works completely on its head, almost as if it's something out of a fantasy. Picture this. In classical physics, if a ball is rolling toward a hill and doesn't possess sufficient energy to reach the summit, it simply won't make it. It will either roll back down or come to a halt at the base. But things operate quite differently in the quantum universe. Rather than having to scale the hill, the ball can sometimes miraculously pass through it, emerging on the other side as though it slipped through a solid object. This is the essence of quantum tunneling. Particles that, by all classical expectations, should be blocked by obstacles can, under specific conditions, appear on the other side. This fascinating phenomenon is only the beginning of what makes quantum tunneling so remarkable. At first sight, quantum tunneling appears to fly in the face of everything classical mechanics tells us. Nevertheless, it is a fundamental component of quantum theory and has been validated by a multitude of scientific experiments. But how is it possible for a particle to traverse an energy barrier it seemingly lacks the energy to overcome? To grasp this, we must venture into the unusual landscape of quantum mechanics. Here, particles don't travel along well-defined paths or occupy exact positions until we make a measurement. Rather, they exist as probability waves, spreading throughout space, rather than behaving like singular points. This wave-like behavior is precisely what enables quantum tunneling to take place. Visualize an electron, for instance, not as a tiny speck in one place, but as a fuzzy cloud of potential locations. Quantum physics uses something called a wave function to describe this spread of possibilities. This mathematical tool helps us determine where a particle is likely to be found when measured. Now, if a particle approaches a barrier, its wave function doesn't abruptly end at the wall. Instead, it begins to decay gradually and can even extend beyond the barrier. This implies that there is a small, but real, chance that the particle could be detected on the opposite side despite lacking the energy to break through. Imagine someone standing before a wall. In classical physics, if they can't jump high enough, they're stuck. But in the quantum domain, that person's wave function stretches past the wall, and there's a slim possibility that they'll find themselves on the other side, almost as if by magic. Such behavior is alien to our daily experiences, which are governed by classical laws. In the quantum world, however, particles exist in a mix of many potential states until they're measured. Among these possibilities are scenarios that seem outright impossible on a human scale, such as particles slipping through solid barriers. The chance that a particle tunnels through a barrier depends on a few key variables: the thickness and height of the barrier, the particle's energy, and the shape of its wave function. The more formidable the barrier, the smaller the likelihood of tunneling. Yet, the chance never completely disappears. This tunneling probability is described by the Schrödinger equation, a core formula of quantum theory that dictates how wave functions evolve over time. One of the most compelling aspects of quantum tunneling is its real-world significance. It's not merely a theoretical oddity. In fact, it plays an essential role in numerous physical and chemical processes. Take, for example, nuclear fusion in stars. Our Sun, and stars in general, derive energy from nuclear fusion, where hydrogen nuclei crash into each other and combine to form helium, releasing colossal amounts of energy. Yet, since these hydrogen nuclei protons carry positive charges, they should repel each other due to electrostatic forces. According to classical physics, they'd never come close enough to fuse. But quantum mechanics offers a workaround. Through tunneling, protons can bypass this electrostatic repulsion and fuse together, even at the relatively moderate temperatures and pressures found in stellar cores. Without quantum tunneling, stars wouldn't shine, and life on Earth wouldn't exist. Quantum tunneling is also indispensable in certain technologies, such as the scanning tunneling microscope, which enables researchers to observe individual atoms. These instruments utilize the fact that when electrons tunnel through a barrier, they create a measurable electric current. This data is used to create highly detailed atomic-scale images of surfaces. Without tunneling, this level of precision would be unattainable. Tunneling is also fundamental in the operation of tunnel diodes and quantum devices, which are widely used in electronics and computational technology. Despite its critical role, tunneling remains one of the hardest concepts to intuitively comprehend, and it often sparks deep philosophical questions about the nature of the universe. If particles can spontaneously pass through barriers, does this imply that reality is fundamentally uncertain? Might particles be flipping between alternate realities? Some interpretations of quantum mechanics, such as the many worlds hypothesis, propose that all possible outcomes actually happen in separate parallel universes. In this view, tunneling is not a law-defying miracle, but a glimpse into another version of reality. While such theories remain speculative, they add a rich layer of mystery to an already puzzling concept. Another key point in tunneling is the role of the barrier's characteristics. The broader and taller it is, the slimmer the chance that tunneling will take place. Still, even with massive barriers, there remains a small, though not zero, chance for tunneling to happen. This probabilistic behavior emphasizes the fundamental unpredictability of the quantum domain. In this microscopic world, certainty gives way to likelihood. We can never say exactly what will happen, we can only predict what's most probable. Quantum tunneling also reminds us that this strange subatomic world plays by entirely different rules. Classical physics is built on ideas like definite location, exact speed, and specific paths. But in quantum mechanics, particles are described as clouds of probability that only become concrete when observed. This strange, rule-bending behavior sits at the core of quantum theory, where ambiguity and randomness reign. Tunneling challenges our perception of how things should behave and highlights the vast contrast between the visible world we know and the invisible one beneath it. In our daily lives, the idea that something needs enough energy to get over a barrier is intuitive. But in the quantum realm, particles ignore these classical rules, leading to the extraordinary effect of tunneling. It's a vivid reminder that our gut instincts, shaped by the world we see, don't always apply at the smallest scales. To conclude, quantum tunneling is a truly bizarre and captivating phenomenon. It reflects the profound strangeness of quantum mechanics, where particles can lead past barriers that should be impassable. From powering stars through fusion to allowing atomic-scale imaging, tunneling is a central and irreplaceable part of our universe. It expands our understanding of nature and underscores the notion that, in the quantum domain, reality operates on a whole different set of principles, one shaped not by certainty, but by probabilities and endless potential. As we continue to explore this realm, quantum tunneling remains a powerful illustration of how much there is still to discover about the fundamental fabric of existence. Among the most fascinating and puzzling ideas in contemporary physics lies a strange form of matter that constitutes nearly 27% of the universe, yet it cannot be seen. It neither emits, absorbs, nor reflects light, which is why it is referred to as dark. Despite being undetectable by light, this elusive matter exerts a gravitational force on regular matter such as stars and galaxies, influencing their movements in ways that defy explanation through known matter alone. In fact, it's this hidden force that prevents galaxies from disintegrating due to their high-speed rotation. Without it, our current model of the cosmos would be fundamentally flawed. The concept of this invisible matter emerged from observations that conflicted with scientific expectations. Back in the 1930s, Swiss astronomer Fritz Zwicky uncovered something peculiar while investigating the Coma cluster of galaxies. He observed that galaxies within this cluster were moving significantly faster than should be possible based on the visible matter present. According to the laws of Newtonian gravity, the galaxies should have dispersed, but they remain bound together. Zwicky suggested that an unseen mass or energy was exerting a gravitational force to hold the cluster intact. He termed this hidden material dark matter, although its actual nature remained obscure. This wasn't the only indication of such a mysterious substance. In the 1970s, American astronomer Vera Rubin analyzed the rotational patterns of galaxies. She studied rotation curves, graphs that display the velocity of stars at varying distances from a galaxy's center. Based on Newtonian mechanics, stars located at the outskirts of galaxies should rotate more slowly than those near the core, due to the gravitational pull being weaker at the edges. However, Rubin discovered that the stars far from the center were moving just as quickly as those near it. This implied that there was additional mass that couldn't be accounted for by visible material, again pointing to dark matter. Given that dark matter does not interact with light or electromagnetic forces, how is it detected? This is where the mystery deepens. We identify dark matter through its gravitational impact on visible structures. By observing the behavior of galaxies, galaxy clusters, and even the overall formation of the universe, scientists infer the existence of this invisible component. Because dark matter influences gravity yet cannot be detected via traditional means, such as photons or electromagnetic radiation, it doesn't belong to the same category as ordinary matter, which includes particles like protons, neutrons, and electrons. So what is dark matter made of? We don't have a definitive answer yet, but various theories exist. One of the most favored theories involves particles known as WIMPs, weakly interacting massive particles. These theoretical particles are presumed to have mass, which allows them to produce gravitational effects. However, they barely interact with other forms of matter, making them impossible to see. WIMPs might be detectable via their subtle gravitational interactions or perhaps through extremely rare encounters with ordinary particles. However, despite considerable scientific efforts using particle accelerators and subterranean detectors, WIMPs have yet to be observed. Another strong contender is the axion, a particle much lighter than WIMPs and originally proposed to address an entirely different physics issue called the strong CP problem. Like WIMPs, axions do not emit light and have very weak interactions, but they differ significantly in mass and behavior. If axions are real, they would be incredibly light, making them difficult to find. Yet their potential abundance might explain the gravitational anomalies seen in galaxies and clusters. Beyond particle theories, some scientists propose that the laws of gravity themselves might need adjusting. One such idea is the modified Newtonian dynamics (MOND) theory, which suggests that gravity behaves differently on vast cosmic scales, particularly near the outer edges of galaxies. According to MOND, what appears to be dark matter might actually result from how gravity functions at large distances. Nevertheless, this model hasn't fully explained all existing observations, and most researchers still favor the notion that dark matter consists of an unknown type of particle. Dark matter's role is also evident when we examine the large-scale architecture of the cosmos. The cosmic web, a massive framework of galaxies, clusters, and interlinking filaments, couldn't have taken shape the way it did without dark matter. In the early moments following the Big Bang, dark matter's gravitational pull helped gather regular matter, allowing galaxies and clusters to form. Without this unseen component, galactic formation would have taken much longer, resulting in a vastly different universe. One of the most persuasive indicators of dark matter's existence is gravitational lensing, a phenomenon predicted by Einstein's general theory of relativity. When light from distant celestial objects like galaxies or stars passes near something massive, the gravitational field bends the light's path. This bending, known as gravitational lensing, allows scientists to chart mass distributions in the universe, even when that mass is invisible. Analyses of gravitational lensing show that galaxy clusters contain far more mass than visible matter can explain, offering strong proof of dark matter's presence. Although dark matter affects gravity, it does not interact with light or other electromagnetic forces, which is why standard telescopes can't detect it. We can't observe it directly, but its effects on luminous matter make its presence undeniable. One of the major hurdles in astrophysics today is that dark matter is everywhere in the universe but simultaneously undetectable using conventional methods. It molds cosmic structure while remaining utterly unseen. An especially intriguing area of study is the potential relationship between dark matter and other unexplained aspects of the cosmos, such as dark energy. While dark matter is thought to make up about 27% of the universe's energy mass composition, dark energy accounts for around 68%. Dark energy is the enigmatic force believed to be driving the universe's accelerated expansion. Some physicists hypothesize that these two phenomena may be related, and deciphering one could help unravel the mystery of the other. More fundamentally, why does dark matter exist at all? What function does it serve in the grand story of the universe's evolution? If we can decipher dark matter's properties, might we also unlock answers to other profound questions, like how galaxies are formed, how gravity works on cosmic scales, and perhaps even what fate awaits the universe? Despite these lingering mysteries, the hunt for dark matter continues to drive scientific exploration. Researchers are conducting experiments aimed at direct detection using ultra-sensitive instruments buried deep beneath the Earth's surface, shielded from cosmic rays. Observatories are scanning the cosmic microwave background, the Big Bang's lingering radiation, for signs of how dark matter shaped the early universe. Meanwhile, theoretical physicists are crafting new models that attempt to integrate dark matter into the broader frameworks of particle physics and cosmology. Dark matter is a cornerstone in the cosmic puzzle. Even though we can't see it, its influence is undeniably shaping the universe in profound ways. When the day comes that we finally identify it, our understanding of the universe and everything within it may undergo a dramatic transformation. Until that time, dark matter remains a captivating enigma, a force that defies visibility but holds the potential to unlock deep truths about the fabric of reality itself. Hawking radiation. Among the most astonishing and paradoxical ideas in contemporary physics lies a phenomenon that offers a fascinating window into the unusual nature of black holes and their intricate ties with quantum phenomena. At first blush, the notion that black holes, cosmic entities renowned for capturing everything in their vicinity, even light, might emit radiation appears downright implausible. Nevertheless, this concept has evolved into a foundational element of theoretical physics, illustrating the deep linkage between quantum theory, Einstein's general relativity, and the fundamental fabric of the cosmos. Back in 1974, the celebrated British theoretical physicist Stephen Hawking proposed a revolutionary idea. Black holes aren't entirely dark. Rather, due to peculiar quantum interactions near the boundary known as the event horizon, the edge beyond which no matter or radiation can return, they can emit a faint glow. This emission, now famously known as Hawking radiation, arises from quantum particle behavior occurring in the empty-seeming expanse near the event horizon. To comprehend Hawking radiation, it's useful to begin with a fundamental quantum concept, the nature of a vacuum. In classical physics, a vacuum implies the complete absence of matter and energy. However, quantum mechanics paints a far stranger picture. According to quantum theory, even a vacuum seethes with temporary, fleeting particles that blink into existence and vanish almost instantaneously. These so-called virtual particles appear due to the Heisenberg uncertainty principle, which allows brief fluctuations in energy even in empty space. Now picture these phenomena occurring close to a black hole's event horizon, the ultimate gravitational boundary. Quantum field theory predicts that pairs of virtual particles, one with positive energy and one with negative, constantly emerge and extinguish each other. But near the event horizon, the black hole's tremendous gravity can separate them before they annihilate. One of the pair may be drawn into the black hole, while the other escapes into the wider universe. To a distant observer, this escaping particle appears to be radiation emitted by the black hole. The particle that escapes carries positive energy, while its partner that falls into the black hole possesses negative energy, effectively decreasing the black hole's mass. This remarkable process lies at the heart of Hawking radiation, energy slowly leaking from a black hole through quantum effects at its edge. Hawking's insight was nothing short of revolutionary. It implied that black holes could gradually shed mass over time. Through continuous emission of radiation, a black hole could steadily shrink. If this continues long enough, the black hole could eventually disappear altogether, leaving behind only the radiation that once streamed from its event horizon. This idea challenges the conventional belief that black holes are eternal features of the universe. It presents a new way of thinking about their ultimate fate. To truly grasp its importance, we must consider the principle of energy conservation. Typically, virtual particles cancel each other's energy as they blink in and out of reality. But when one falls into a black hole, carrying negative energy, and the other escapes, the total energy of the black hole system decreases. Over time, this causes the black hole to lose mass, a process central to the concept of black hole evaporation. The possibility that black holes can diminish and eventually vanish has deep and far-reaching implications. It suggests that black holes, even the largest ones, might not be permanent after all. Instead, they could eventually dissolve into faint streams of radiation, no matter how massive they once were. However, despite being theoretically robust, Hawking radiation has not yet been observed. One of the primary challenges is that the radiation from a typical stellar mass black hole is incredibly faint, so weak that current instruments can't detect it. Tiny primordial black holes, which may have formed early in the universe and would emit much stronger radiation, may have already evaporated entirely, eluding detection altogether. Despite this lack of direct evidence, the concept remains vital due to its implications for our understanding of information and the core principles of physics. One of the most puzzling aspects of black hole evaporation is its link to the black hole information paradox, a mystery that has troubled scientists for decades. Quantum theory asserts that information about a system's initial state cannot be lost. But if a black hole evaporates fully, what becomes of the information that entered it? Hawking radiation, being random and seemingly unconnected to the black hole's interior contents, appears to offer no clue. This apparent contradiction threatens the principle of information conservation, leading to the enduring black hole information paradox. Some researchers speculate that the key to solving this paradox lies in the nature of the radiation itself. One hypothesis, known as the soft hair theory, posits that information isn't lost but encoded subtly in the emitted radiation. This implies that black holes may harbor more information than previously believed, information potentially woven into intricate correlations within the radiation. If this theory holds true, it could resolve the paradox and deepen our understanding of how quantum physics intertwines with gravity. Furthermore, studying Hawking radiation may shed light on the deepest architecture of the universe, potentially revealing new aspects of quantum gravity, a unified theory that links the macroscopic world of gravity with the microscopic domain of quantum particles. This unification remains one of the most important goals in physics. Hawking radiation offers a critical avenue for exploring how gravity, which governs galaxies and planets, interacts with quantum phenomena, which dictate atomic and subatomic behavior. Hawking's idea also influences cosmology and ideas about the ultimate fate of the universe. If black holes can evaporate, it suggests a future cosmos free from these colossal objects. Instead, the universe might one day be filled only with the faint relics of black holes, subtle streams of radiation echoing across the void. Some models suggest that once a black hole vanishes, it might leave behind a tiny, exotic remnant, perhaps a Planck-scale particle or another unusual object that could play a role in the next chapter of cosmic evolution. Though we have not yet witnessed Hawking radiation firsthand, the concept stands as one of the most influential in modern theoretical physics. It has transformed our view of black holes, the preservation of information, and the fundamental laws that shape reality. At the intersection of thermodynamics, general relativity, and quantum mechanics, Hawking radiation offers a compelling glimpse into the forces that sculpt the universe. As research into black holes and space-time deepens, Hawking radiation will undoubtedly remain a central pillar in the ongoing quest to decipher the most profound secrets of the cosmos.